OK, so one of the goals of the workshop was also to give you an idea on how you will be ready to propose for time for DKIST. And the part of that process is also learning how to use these instrument performance calculators that will be able to tell you whether the science that you want to do is doable with that instrument, with that cadence, with that resolution, and so on. We have software calculators, simulators for all of the instruments. Like Valentin mentioned at the beginning, they all start from the flux from the sun, and all that process of getting the flux to your instrument, taking into account the telescope and all the optical elements and so on. And on top of that, they put the details of the instruments itself. You have n mirrors to get to the Coudet table, and then you have each instrument has a lot of other elements inside. So you remember that, do we have a pointer? Yeah, that we have the Coudet table with the 4 instruments that can work together, and the ViSP is down here. You can already sort of see in there is 3 separate arms. This is another representation of the instrument itself. So it's what we would call a classical spectrograph. So diffraction grating-based spectrograph has got a slit. It can access the full visible near-infrared range, as we said on Tuesday. And it's got 3 distinct arms. It's 3 mechanical positions where you have 3 cameras, and you can fit them with equivalent optical elements along the path for each of them. You can fit them with different wavelength ranges. The interesting capability of ViSP is that there isn't, it's not that this is always in the blue, this is always in the red, and this is always whatever. Depending on your lines, any line can fall in any of these 3 cameras. And that is one of the elements of the IPC of ViSP, that you can select your lines and see if you can look at them all, up to 3, of course. You can put only 1 if you want. But sometimes H alpha will be here, and sometimes H alpha will be here, depending on what you're combining H alpha with, right? They have different scales. So some of them have a longer, they have a different spatial scale. So that the same amount of pixels will be this long in one arm and this long in another arm. And different spectral resolutions and so on. I mean, not tremendously different, but different nonetheless. The width can be changed depending, again, on your science. You can go from the super high resolution one to another one which is maybe optimized for having a lot of photons, again, depending on what you want to do. It's a dual beam polarimeter, so that at once it images the I plus Q, I minus Q, or whatever combination of the Stokes parameter you're doing. And that means their split is done in the wavelength direction, so that if your detector is this long and the spectrum will be 20 angstrom, you really can use only 10 angstroms, because the other half of the detector is devoted to the other state of polarization. And it doesn't have a slit jaw proper, and it uses the VBI blue channel for context. And this, there will be a lot of work to determine how this is going to be done in practice. I think this is a little movie just to give you a sense. So at any position, once you recalibrate the data, you have your intensity and your Stokes parameters, so the I, Q, U, and V. And if you notice here in this 3rd dimension, like this diagonal, you have an image that forms because you're scanning the image, so that you have a slice and another, and eventually you get to a spot. And these are some of the characteristics. I don't want to go into them. They are all in those summary documents that you have in your folders, so you can find them. Yeah, one thing that I didn't say the other day, I have put the actual software for the ViSP in that common folder. I have not put the other ones on purpose, because we want, in a sense, to keep control of the versions that are often updated. And so we want to have the new ones always from one page, which is listed in my talk. So you can go there to get the updated versions. I put the ViSP in the common folder because it was easier for today, but just remember that. OK, so that's about it. You remember that it can choose, you can pick any line within the full spectral range. And also, this is a slide from the other day. Remember that if your science requires 2, 3, 4 different selections of wavelengths, you cannot do that all in one day. You have to, if you're changing the wavelengths on any of the arms, you should plan on doing that in successive days. This was for the field coverage. So these are the 3 arms. They are 75, 60, and 50 arc-second long. And they all point together, of course. And they all scan together, and they can scan up to 2 arc-minutes. Because that is the maximum field of view allowed by the instrument itself. If you want to go here, you have to repoint the telescope. OK, so this was the summary, which is also down there. You don't need to read it now. So for now, the calculator is written in IDL. It's a GUI. So you will have to do it. I don't know. Do you have the software? Did you download it? Or if we wanna try it together. Or you have to go into that machine and just, if you just do IDL and then you do this, then you don't have to do anything else but click. So that seems easy enough. Let's try a few minutes, and I'll do it myself. So this is the kind of window that you will obtain. Oh, it doesn't change. OK, kind of tiny. If I put it bigger. Let's see. Oh, come on, look at this. It doesn't give me an option. Nope. Doesn't. Where is it? Display. OK. Where do you see it?
At the very top. Optimize for the drawdown menu, custom.
Creston?
Oh, actually, right below that, it's scale.
Scale. Oh, OK. Oh. Let's try it. Well, that would be the same, right? So, what one is?
Gianna, where do we download this from?
And this is too much. The other is too little, and this is too much. Nope. So I don't know. Do you have a very last one? Why doesn't this go away? OK. I'm always losing the last ones, but that's OK. I mean, I can give you examples just for the first two windows. So
someone was asking, where do you download?
Yeah, it's in the Google Drive folder that was, if you want to use it on your own laptop. Yeah, just download the whole directory. You'll find both the presentation, the slides, and the software. Then go into that directory for simplicity. Did anybody manage to get here? Not yet. Nope. You can log in into that IDL machine that we had the other day. Let me go by. Let's see. Did you get back your adapter?
My adapter is floating around. Claire?
Claire took it? Okay.
Where have it?
That's okay. I mean, so you don't lose it, right? And to keep track of what it is.
Ah, okay. Yeah.
Yeah. Claire has it? You give it to Claire. You give it to Claire.
I wanted to leave it there.
I'll find out.
Okay. So does it work for you? Oh, yes. Okay. So one is working. How about others? 2, 3, 4, 5. Oh, okay. So more than, let's see, my first row here. There you go. Will take some time.
Sure.
Yeah. Excellent. Tell me.
When are you breaking for?
In about 20 minutes or so.
Okay.
Yeah. You don't need to listen to all of this, right? You know it by heart.
Find my adapter.
Okay, so this is the default page that pops up, and now from now on it's all clicking, right? So the default configuration, but that's just because we liked it, shows you the 3 arms with 3 different lines. We have H alpha, we have calcium K, and I think this is 8542. So this is calcium 2 infrared, calcium 2 resonance line, and H alpha, right? Of course, the ViSP is the instrument that you will use to do your strange things, right? You want the lines that are most sensitive to the Hall effect, or you want the full Balmer series. Well, you can't. You have only 3 ranges, or things like this. So you want to change this selection. And the way to do that is you go up here where it says optimizers, and you click it. And there is a new window that comes up where you can select your own wavelengths. So you can select 1 line, 2 lines, or 3 lines. Actually, you can probably select more than 3 and then tell the software, find all the possible combinations of these 5 in triplets, of course, because you can observe only 3 at once. But say that you're interested in all of the Balmer series, and then say, find me the possible combinations, and then you decide whether you want H beta together with H delta together with H epsilon, or whatever, right? Let's keep it simpler, and let's go to 3 lines, and let's do the Balmer series. So H alpha, H beta, 4861. It's in nanometers, so you have to put the comma in the right place. And then H, what's next? H gamma, 434.0. It doesn't matter if you put one here and the other here. The optimizer will do the numbers nonetheless. You know, it will find the best combination no matter where you position your line. So after you select the wavelengths, you go up here and you say, OK, do your job. And it works. It starts working. And if it finds a combination that might work, like it seemed it did, it tells you here. So yes, it did find a possible solution. And so, OK, show it to me. And go to the load so that these 3 things will change. So H alpha stayed in the first? No, it didn't. Where did it go? I guess that this is H alpha now, and this is H beta, and this is H gamma. So he decided that in the first arm, it was best to put H gamma. In the second, it's H beta. And in the third is H alpha. And up here, this is the window of the other parameters that you will have to choose. And these are the windows that will tell you what kind of results you get. Well, it's a little bit mixed. So we've chosen the wavelengths, first thing. The second thing to choose is whether you want polarimetry or if you want intensity only. Numbers will change because the way that the data is taken changes. But let's stick with polarimetry, which probably will be the default way to use it. The grating is fixed. I mean, there is a button there, but it won't change anything. The tilt angle is best if you leave it alone. Yeah, it's a grating, so if you tilt it a little more, it will move the spectrum, right? You might see if that helps you, because instead of wanting all of this, you will want from here to here, for example. That might help you. Another way to do that would be to put, instead of your central wavelength, this one, to put this one. That will be equivalent, probably. Then you can select your slit. And again, this needs to be optimized to your science case. For example, if you're looking at things only in the far red, having the smallest slit doesn't make much sense, because the diffraction limit is anyway bigger than that. And so you're just starving yourself of photons that you could be using in a different way. This is the slit step parameter to do a raster scan if you want to do a raster scan. And so up to you whether you want to match it to the slit size, so you do contiguous things, or if you want to do big steps. You know, you can actually write whatever you want in there. So let's say I want to do a very big step, like 1 arcsecond. I can do that. Why not, right? How many of these steps you want to do? You want a big raster or a small raster? If I put 1 arcsecond, and here I have 1,000 of these slit positions, then I have a width of my map of about 1,000 arcseconds, which is obviously way too big for the field that I have. So it doesn't crash, but it won't make much sense. So here maybe we want to do 100, because that's the maximum that I can scan. 120 arcseconds is the maximum I can scan. Here, if you want to repeat this scan at 1 time, 2 times, 10 times, as much as you want. And here, where you plan to be on the sun, this essentially will change your intensity at the source, because if you go towards the limb, you have a darkening, so that there is less photons, and it will take that into account in the calculations. Let's leave it at this center for now. Then you have to decide how long you want to integrate. And you know, this is how much you integrate at any slit position. And that will change your signal to noise, like Valentin showed. If you integrate for longer, you will have a better signal to noise. If you integrate for shorter, it will be noisy. On the other hand, if you integrate for longer, it's going to take you much longer to do all your stuff, right? And the modulation states, I don't know why they decided to go in this software with a default of 10. I think that the default should be 8, like Christian was talking about yesterday. And so on. And so here are some of the results. It would take you 9 minutes to do that map. Since we did it only once, that's also the cadence and also the total time. And this is the data rate and the data volume. This is not one of your bad instruments in terms of data rates. You can imagine, I mean, those are the VBI and the VTF. Those are the ones that will produce a large volume of data. Here you have some results for for each single arm. I wanted to show you a couple of numbers. Let's see, the other day when Valentin was discussing all this Flux budget, he said that at the end of the story, your efficiency is very low, like the order of a few percent. That's what we were saying. And indeed, here the system efficiency, considering everything, is about 2%. And this arm is a bit better, but not by much, 2.6%, just to give you an idea, right? What you're interested in here is your signal to noise in the continuum. That is what he was discussing. That is the number that we often use to define how good or bad are the data with respect to what we want to do. And actually, it's also plotted in the plots themselves. So this is intensity normalized to the continuum. And this is the signal to noise. And if you see the blue line, that would be the signal to noise for the I, Stokes I. The dashed blue line is the signal to noise for the QUMB. The number this number, 18, what was it? 1868, 2000, whatever, that refers to the blue line, to the blue continuum line, right? And that is what we usually work with. What else to tell you? So this is the 77 arcsecond long slit. And this is the, I think the instrument theoretical resolution at that wavelength. Instrument plus telescope, of course. Theoretical resolution of that wavelength. And I think that your, what is this? Spectral and so on. Spatial full, so, and your pixel size is about 0.3 arcseconds. So you are sampling at the limit. This is half of the resolution that you will actually get. This is the best that you can do. This is explained in the manual. I don't like it particularly because nowhere they tell you what the pixel size is. They tell you what the instrument would be able to do if everything would be perfect. They tell you what is the spatial resolution of the, what is this? The spatial sampling. These two together makes for the spatial scale, but frankly, I do not remember how that goes, so you should be looking. And this is the spectral resolution that you achieve. And you can see how many pixels you're reading out of the detector, how many angstroms that is. You can change that a bit. For example, you can introduce binning. That is done on board, on chip. And that, of course, reduces your resolution, but increases your signal to noise. So you can play with all these parameters. And then when you're done, say that we do 10 repeats or so, you just save it, and you give it a name. And this is one of the things that you will have to attach to your proposal. Does it make any sense? Will you try to play with it tonight? You really can choose any line, even the most exotic lines and so on. One thing that the simulator does not do is considering off-limb. It doesn't have the information in the background to give you a reliable flux for off-limb features, even though you could, because there are several, well, you could, for example, just look at H alpha in a prominence. I mean, that's obvious, right? But it doesn't have the machinery behind to do that yet. And you could also look at some coronal lines. There are several coronal lines in this interval that one could use. They are the ones that have been used for decades before we invented satellites. OK, any question? Yes?
What will the readout time be?
Say it again.
Readout time?
Readout time. Oi. Let's see, this is a different camera than the other ones, so it will be a bit slower than the other ones. But I think that you can, there. Frame rate, this is the maximum you can do, 50, I think it's 50 hertz maximum. This,
That includes the readout time and everything?
I think so. And also the time to move the slit is of the order of 0.1 seconds, maybe. So when it does the number of how long it takes to make the map, it counts that. So probably, I would say that for fast acquisition, your map rastering overhead is probably bigger than your acquisition time. And I think that there is a duty cycle, right? A duty cycle will probably tell you that. If you have something that is fast in acquisition, but you want to do a big map, that would probably go down. OK.